So we'll continue today's class, and we're gonna talk about some stuffs that we have to discuss today. Uh, First of all, the thing that I would like to pick up is from this equation, the double-slit experiment. Uh, this was the formula for how the double-slit experiment actually works out for 4 different variables, lambda equals to x by d. And one more thing that I'd like to talk about is that how can two different type of wave can have two different type of attenuation symptoms. Now, first of all, I'm going to start with the idea of attenuation. Attenuation, that's the spelling, ATTENUATION, attenuation. Attenuation means the gradual energy loss of a wave as it travels from the source further onwards. So whenever any wave is sent out, it can lose energy. Actually, it doesn't actually lose energy. What do we mean by attenuation is that the reduction of intensity. Well, let me just define intensity first. Intensity of a certain wave is given by power per area. Now, power in this case I can write as energy transferred over unit time per unit area. So that's basically the idea of intensity. The unit of intensity is watt per meter square. That is the SI unit. What this means that if we set up a certain surface to capture the energy available from a certain source, how much joule per second of energy is available from that source at that location for unit square area. Now, one thing is very important for us to understand that. Let me just show you image. So this is actually one of the images that I can show you. What you can see in this within this image, that if we have a source of a certain power, in this case they say strength, that let's say the power of this source is, let's say, 100 watt, which means it is emitting 100 joule every second in a spherical direction out of its path. If we consider different distances, for example, let's say this is a area of a area at a distance r from the source, and within this area, the amount of energy that is coming out within this three-dimensional angle, let's say that is some amount of energy per second, and this is falling onto this much area. But if we take this, if we want to measure this at twice the distance from the source, that surface area simply becomes 4 times as much. If we go for triple the distance, that same area becomes 9 times as much. The idea is that as we go further and further away from the source, with respect to the distance, the area actually becomes related to the square of the distance, because the area of a certain sphere is given by 4 pi r square, where r being the radius of the sphere. So if you have a sphere of r radius, if you have some area of it, if you have another sphere of 2r radius, that's gonna have the 4 times the area of that. So same amount of energy is getting spread out. That spreading effect actually causes the intensity of a certain source to be less at that point. Now, it's very important how you express this term. Intensity of a certain source should be measured at a specific location. For example, if I just try to draw it, where is the, yeah, let's say here is the source that has a starting power of, let's say, P. And then let's say at this distance, we are receiving a fraction of that power, because this power P is actually spreading out in radial directions in a spherical way, not in a 360-degree direction. It's emitting out in a spherical direction. Like this point source can be considered to be a celestial source, like a sun. When considered for a very large amount of distance, the sun can be hypothetically considered as a single point dot, which is a very oversimplified simplification, but that's how we usually approach the problem solving for physics, that for required cases, a cow can be considered to be a sphere and something like that. So if this source is emitting of some amount of power P at a certain distance, if we go over here, let's say this distance is R, let's say the power over here drops by a certain fraction. Let's say this is let's say this is another power, that is P prime. Now, obviously, P prime is significantly less than P because we are considering the intensity at a certain distance, so the power has spread out. And then if we consider the intensity at this point would be, let's say, the amount of power received over per square feet area. So if we have some area over here, we're going to receive a certain intensity within this surface from the source. If we get further away, then we're going to receive even less amount of power for the same amount of area because the power is splitting up. This is one of the reasons that this is one of the primary reasons that intensity as we go further away from a source that slowly becomes less, which essentially means that we are going to be receiving less and less amount of power from the source. That's one reason. The second reason is that if there is a medium in between the source and the observed location, if there is a physical medium, as the wave travels through that medium, it's going to lose a significant portion of its energy, which will be absorbed by those medium particles. For example, if you consider for the celestial case, which is the distance, the gap in between multiple objects, for example, the significant space from the sun to Earth is actually vacuum. So we can consider that location within this space, we don't have any medium related reduction of energy. But if you consider the energy transfer to atmosphere from let's say across 1 kilometer distance, as light will travel through the atmospheric particles, many of the photons of the energy would be falling onto the atmospheric particles, for example, the molecules of nitrogen, oxygen, carbon dioxide, and the dust particles, and the humidity water particles. So these will also absorb a portion of their energy, and that will also cause a significant lowering of this energy. Now, the effect of the medium is somewhat really dependent on what type of wave are we considering. Now, one thing that I need all of you to understand, that this idea of intensity given by area, which this can be actually further simplified like this: I equals to P divided by 4 pi r square. 4 pi square is the area of a circle, which ultimately leads to the relationship of the inverse squared law for
Sir, W meter per second W meter per second.
Oh, this is the unit of the intensity, watt per meter squared. Power unit হচ্ছে watt, area হচ্ছে meter square. This is the unit of the intensity quantity.
So, sir, because wave spreads, the area becomes greater and the intensity of the wave decreases.
Precisely.
And the other reason is the medium particles.
The medium part, exactly. Two different factors I'm trying to highlight here. So for the exclusive reason of the spreading out, the intensity of a certain intensity at certain locations can be very easily dictated by this proportionality, I proportional to 1 by r squared. This is called the inverse squared law for distance for intensity reduction. This will always happen for a source that is emitting energy in 60 degree or in all directions. This will always happen. This is exclusively not a case for lasers. Now, lasers are very unique because lasers are made in such a way that they will not undergo spread out. The way any laser work is that if we have a laser source that is aimed in this direction, and this is the amount of size of your output hole, the laser beam is going to go straight and it will not spread out. It will not spread out. That's not going to happen. That's how lasers are designed to work. So
why are they like this?
Sorry?
Why are they like this? Why won't they spread out?
Because lasers are made that way. Made that way means when lasers are made using convex. They're made by using a convex lens, where the source is actually placed at the focal point. So the beam that comes out actually become parallel of each other. So they are not actually dispersing out. Lasers are made that way within the device, so that the intensity or the strength of the beam actually remains almost identical as long as it actually hits any solid barrier, or as long as it does hit somewhere. That's why lasers don't have that problem of spreading out. That's a very exclusively a unique case, but for all other typical energy sources, energy is spread out in all directions because we don't have the artificial mechanism to concentrate the beam so that they would be definitely parallel to each other. I mean, what I'm trying to mean is that whenever any regular source is emitting out energy, it is emitting out energy in a diverging pattern. But laser devices produce laser in a such way that the beams or the individual photons which make up the laser beam, they all go in a very straightforward direction parallel to each other. So the spreading out is not a case for laser. Okay, but we can have physical mechanism that is going to cause the spreading out of laser, which I'm going to discuss after a while. So this is one of the factors that accounts for the reduction of intensity. This is also one of the reason why where is that image, why whenever we have the light waves producing a double-slit experiment fringe pattern, we have the fringe pattern that looks like this. At the center, we have really bright fringes, but as we slowly go further away from the central maxima, you can see that the dark spots are pretty much dark. I mean, dark spots are all right, but the bright spots slowly tend to lose their brightness. You can see that as from the central maxima is the brightest dot, and as we slowly go further out, the maximas are slowly becoming less and less and less bright. The reason is that the interference is happening just the same way, but the point is the amount of individual amplitude that meets at the central maxima point, that is the of maximum size. As you go further away, so for example, if you start from this source, as you go further out and further out and further out, these beams has to travel a much longer distance compared to the distance they had to travel for the central maxima, and that further out distance traveling causes them to scatter more. So the amplitude of the individual light rays that falls onto different parts of the screen, that actually becomes smaller. Now, the reason the dark parts remain perfectly dark, because both of these waves have more or less the same amount of reduction in case of the dark spots, or in case of the for the case of the minima positions. For example, if I try to give you some mathematical reasoning, let's say at the center for a certain experiment of double-slit experiment, let's say at the central maxima, the individual amplitude of the wavelengths were 10 centimeter each. I'm just assuming this number. No wavelength should have, I mean, it's almost unrealistic to have 10 centimeter, but I'm just picking 10 centimeter as an example. So if you have an amplitude of 10 centimeter at the central maxima, which means the total resultant amplitude for the central maxima would be 10 plus 10, that gives you 20 centimeter of total amplitude. So that gives you a really bright dot. But if you consider, let's say, somewhat significantly farther away from here, let's say somewhat over here, let's say we have a bright spot right over here. So let's say within this bright spot, the amplitude of both of the amplitude of light that came from both of the sources, they got lowered by significant amount. Let's say over here, the individual amplitudes are 6 centimeter and 6 centimeter each. So they're pretty much the same amount. There'll be a slight variation between them, but approximately at the central maxima, they would have the pretty much the same amount of amplitude. So the total amount of amplitude that you're going to get for the central maxima position is going to be 12 centimeter only. So what I'm trying to tell you is that you're still going to have a bright dot at the maxima position, where you have the same phase of the light waves merging with each other. But that total resultant amplitude is going to be significantly smaller compared to the central maxima. That's why you are losing the brightness of those spots. However, whenever you are considering for the minimum positions, let's say if I try to give you an idea for at the first minimum position, let's say at the first minimum position, the two amplitudes are still 10 centimeter and 10 centimeter, but because they are merging at opposite phase, they're practically canceling out each other. So you have a total resultant amplitude resultant is 0 centimeter. That's what is happening close to the central maxima. If you go for consider for the further out, for example, let's say the location where you have the amplitudes of 6 centimeter, let's say the very next dark spot, or the destructive superposition location, you have also 6 centimeter and 6 centimeter. Both of them are 6 centimeter, but they're canceling each other out because of the destructive interference. And at this case, you are still getting perfectly 0 centimeter of remaining part. What I'm trying to mean is that canceling, whenever they're canceling out, they're canceling equal amount of smaller amplitudes. So that's why the canceling out happens almost perfectly. But the merging actually lacks significant amplitude compared to the central maxima, because both of the individual amplitudes coming from the sources, they're individually smaller, so that you do not have as much brightness as the central maxima part, where you had a significantly bigger amount of amplitude. So that's the reason that all the dark spots pretty much appear perfectly dark, but all the bright spots, as we slowly start to observe further away from the central maximum position, they tend to lose their brightness because of the effect of lowering the amplitude, because the light rays have to travel further away, they spread out more, which in other words, simpler terms, we say the effect of attenuation. এই পার্টটা বুঝা গেছে কিনা? Any question?
ইয়েস স্যার, স্যার মাঝখানে ক্লাস গ্যাপের জন্য আগের জিনিসগুলো রিকল করতে পারছি না স্যার।
Oh, আগের জিনিসগুলো খুব simple. If I want to help you recall a little bit, is that light rays get divided. We actually split one source into two different sources so that we have them in coherence, so that they would have a constant phase difference across each other. And because the light rays would have to travel different distances for meeting onto the screen coming from two different sources, they would have different path covered. So depending upon how much path they have covered, they can either meet at perfectly synchronized with each other, which we call the constructive interferences, or they can meet at perfectly asynchronized of each other, which we call the destructive interferences. So locations where they meet perfectly constructively, which we call those points the maxima points, where we'll have really bright light, and locations where they meet perfectly destructively or perfectly out of phase or with 180-degree phase difference, they will perfectly cancel each other out. And for all the points in between, we're gonna have a partial illumination. So we are not going to have, let's say, one bright dot and then perfectly darkness and then another bright dot. No, it doesn't work that way. You have a really bright location, and then the brightness slowly dims out, and eventually you have no light, and then it slowly brightens out, and then you have another bright location. So you have a mixture of constitutive and destructive in between. Locations where you get the most bright regions, those are the locations which you call the maximal positions, where we have the perfect merging of the same phase waves, which perfectly merge with each other.
Oh, sir, is there any gap in this region, or is this just a pillar?
Which region?
স্যার ইন্টেন্সিটিটা কি মিডিয়ামের ডিসটেন্সের মানে মিডিয়ামের রেজিস্ট্যান্সের জন্য কমে আর এরিয়া বেড়ে যায় তাই?
অ্যাটেনুয়েশন যে হয়, মানে একটা সার্টেন সোর্সে ডিফারেন্ট ডিস্টেন্সে যে ইন্টেন্সিটি কমে যায়, তার একটা এফেক্ট হচ্ছে স্প্রেড আউটিং এফেক্টের জন্য। এখন আমরা এই স্প্রেডিং আউটটা আমাদের এই লাইট সোর্স গুলাকে সিগনিফিকেন্টলি এফেক্ট করে, বিকজ দ্য স্প্রেডিং আউট ইফেক্ট ইজ same for all type of sources, whether they are electromagnetic sources or they are mechanical sources. Mechanical sources means, for example, sound wave. So the effect of spreading out, or I proportional to 1 by r square, which I showed you a bit earlier, that inverse square law is equally applicable for all type of wave sources which have a diverging ray type of spreading out, unlike lasers. আর ইন্টেন্সিটি কমে যাওয়ার মেইন কারণটা হচ্ছে যে সেন্ট্রাল পয়েন্টে total distance covered from both the sources are actually very small, because this point is really close to the source. But as we slowly go further and further out, those points are altogether further away from the two sources. That's why their light energy significantly reduces, almost by equal amount. So the sum actually becomes less for bright points, and the subtraction still gives you 0 because they are almost equally amount less. I'm not sure if I answered your question. Could you tell me the question again?
Sir, I asked whether intensity কমে যায় because of the medium resistance or because of like it spreading out and the area becoming larger.
Both of these factors affected. Medium resistance affects more for the mechanical waves, for example, a sound wave. Medium resistance affects significantly less, which are electromagnetic waves, which do not require the media. So the part that I'm trying to explain over here for the case of light waves, the spreading out of the medium, the in attenuation due to the medium is almost not present for this example, because light rays are very nominally or very marginally or almost not affected by the presence of atmosphere, almost not affected. I mean, if I have to say exactly to itsy bitsy parts, are they affected by the medium? Yes. Is it a lot? No. So for light waves, the spreading out due to the attenuation due to the spreading out is the key factor. But I'm going to describe for the sound waves just after a while, in which case both the spreading out and the medium dependency, they will both play a very significantly strong role. Any further question? এই ডিমিংটা কেন হচ্ছে এটা প্রপারলি বুঝা গেছে কিনা সবার?
Yes, sir.
Yes, sir.
সাউন্ড ওয়েভস এর জন্য যে জিনিসটা হয়, আমি একটা লেট মি জাস্ট গ্র্যাব ওয়ান ইমেজ।
স্যার, আজকে আমাদের স্কুলে বলেছে যে নয়েজ ক্যান্সেলিং টেকনোলজি ইউজ দিস ডিস্ট্রাকটিভ ইন্টারফারেন্স।
Yes.
So sir, like how do they exactly do it? Like, do they play the same audio over again over the same clip so that there's a destructive interference, or they play a reversed clip where there's a constructive alternate where there's a chance to be reverse the amplitude direction, like that, sir?
Somewhat similar. আমি বলতেছি একটু পরে, দাঁড়াও। সাউন্ডের গ্র্যাজুয়াল মার্জিং এর ইন্টেন্সিটি ফিগারটা গেছে কই? Can find it in the net. Yeah, this is the one. So actually I opened 3 images, I believe, or I didn't. Okay. So the reason I have all of these individually different images is that if attenuation did not happen, which actually happens, but if attenuation did not happen, if attenuation was not a thing that we had to consider, then this is how the intensity would look like. I mean, if we consider that if I try to plot the intensity value of all the individual different points along the screen, at the central maxima you have some intensity which is pretty high, highest, and then you slowly lose the intensity and you have zero intensity at the dark spots, and then you increase it once again and you have a large intensity at the or bright spot at the next maxima, and then you have zero, and pretty much all the maxima points would have the same intensity. If attenuation was not a factor, this is the type of graph we should be expecting. This is what we call intensity graph with respect to the distance on the screen. But because intensity happens, this is the type of graph that we get. So we have highest, brightest location at the center, and all the dark spots are perfectly dark. You can see that for all the points where we are supposed to have destructive interference, this intensity graph is perfectly reaching the x-axis, or it is reaching to the zero value. But for all the points which are supposed to give us dark bright spots, they don't give us perfectly of equal amount of the central maxima. They give us significantly less, and you can see pretty well that this graph is mirrored on both positions, because you should understand obviously that whatever happens at the bottom, the likewise it happens on the top. So this graph is actually bisymmetric, but you can see that there's a gradual decrease of the bright points intensities. So as you slowly go further out, this thing slowly becomes less and less bright, pretty much what we have seen in this figure as well. This, oops. So yeah, pretty much what we can see in this figure, which is an actual captured image for the double-slit experiment. As for the sound, this is the MCQ that we need to consider. This image is actually pretty small. So let's say if we just plot it over here. I think copying from here helps us a bit better. Let's have a look at this MCQ. This is actually an MCQ from your syllabus and from your year. So try to understand how this should work out. Have a look. Two identical loudspeakers are connected in series to an AC supply as shown. Identical loudspeakers, which means in this case we are producing sound waves, and they are connected from the same AC supply, means they will be in coherence with each other. So these two are coherent sources. Whenever the AC supply is giving us positive amplitudes, they are both going to make sound, and whenever it is going on the negative side, they're both going to produce rarefaction. So the key reason that they're both operated from the same AC supply is to make sure that they are perfectly coherent with each other. We don't have any frequency variation between them, and we are using loudspeakers. So in this case, the observed wave would be sound waves. So these two sound waves will be these two sources are producing waves in both directions, and this XY is actually not a screen. This XY is actually an imaginary line along which a microphone would be moved along. A microphone would be moved along. So what I'm trying to mean is that let's say we have a microphone, and that microphone is connected to a CRO device, and we're going to move this microphone along this line to find out at which locations we have maximas, at which positions we have minimas, and that can give us the that can help us to figure out where these things are. If you don't want to use a microphone, or if you don't have the opportunity to use to have a CRO to visualize the wave, actually we can also use a human ear. Human ear means that we can make a vertical line using some plumb line or something like that in front of the whole setup, and make a person slowly move their ear. I mean, having one ear closed, they should use the other ear, because using both the ear will definitely give us a mixed signal, because we want to use one detector. So we should close one ear completely, and using the other ear, we can move our head along this line and try to figure out at which locations we hear a loud sound, at which locations we hear silence. And this is something that we're trying to achieve within this line. The question over here asks that which graph best shows the variation of intensity of sound with distance along the lines XY. So how would the sound intensity look like for this case? Now here's the deal. This is not supposed to happen, because here it shows what? That we are never going to get silence. Now, do you get my point?
No, sir.
This is showing that we are going to have ups and downs of the intensity, which means we're going to hear loud and we are going to hear less loud sound. But at no point are we going to have any silence whatsoever. We are not going to have silence. We're supposed to have silence, because at certain points the waves are going to cut with each other with opposing phase. So having no silences is actually doesn't make sense, because the way, I mean, these graphs, you have to understand, this XY line over here is shown vertically. Here the XY is used as the x-axis. So this whole thing is actually rotated by 90 degrees. So the graph is actually, graphs are supposed to show, I mean, what they're trying to show us is that should the intensity versus the curve should look like this or not. I mean, you need to assume this thing on this part. Buchke will say XY is the line, and in this case XY is the horizontal axis. So how would the intensity look like? Let me elaborate you. This is the intensity axis, this is the distance axis. What this is actually showing us that I mean, যখন x থেকে y এর দিকে আস্তে আস্তে microphone move করবে, as I'm going to slowly move the microphone, I should be able to observe an increase in intensity, and then a maximum intensity at a certain point, then a decrease in intensity, and then there should be a minimum intensity, but not perfect silence at a certain point. Then the intensity should start to increase. In this case, the word intensity should translate into loudness, because for sound, what is the intensity? I mean, for light, the intensity is brightness. What should be the intensity for sound? What do you think?
Sir, pitch.
No, not pitch. It's the loudness. Two waves canceling each other out. So you're having no waves remaining. So you are not going to hear the sound. Two waves adding on to each other. So you are having a much bigger amplitude. Bigger amplitude leads to what property of the sound? You have learned 3 different properties in your O levels: pitch, loudness, and quality. So amplitude affects which of this property? Loudness. So locations where you are, we are having constitutive interference, so constitutive superposition, those locations we should hear a pretty loud sound, and locations where they are merging deceptively, we should hear a pretty low sound. So this is where so that's what they tend to show us, that we should have a gradual change of the intensity. In this case, the intensity can be translated into within your head as loudness of the sound. So should we see a figure intensity variation like this, or should we see an intensity variation like this, or like this, or like this? Now let me help you to understand this whole question. Let me explain first, then you can give me your ideas. If attenuation was not a thing, if attenuation did not happen whatsoever, this would have been the correct choice, right? We have loud sound, perfect silence, loud sound, perfect silence, loud sound, perfect silence. So we have equal loudness at all the constitutive points and perfect silence at all the destructive points. This would have been the case if attenuation did not happen. Do I make sense?
Yes, sir.
There would be an even distribution across the entire length. But attenuation does happen. So for light, this is the scenario. So we have loudest sound at the central maxima, and then the maxima slowly lose their loudness, and we also have perfectly destructive sound over here. Now the thing is, should this be the correct answer of this question? The answer is no. The correct answer of this question is actually this. No, let me explain why. For this experiment, we are using sound sources. The attenuation of sound sources will be significantly affected by the medium that is present in between, which is obviously air. How does the air molecules attenuate a sound wave? Try to understand. Whenever a sound, I mean, you have to, okay, let me just tell you some sentences, and I'm gonna say it slowly, and I want you to understand and visualize this thing. Let's say we have some atmosphere. Within this atmosphere, the particles are moving in random motion, Brownian motion, that is. So they are not all stationary. They are all moving in random erratic motions in all different directions. Whenever we set up a sound source, let's say on the left side of the atmosphere, it produces a controlled, disciplined movement of the air particles down the path. Some air particles, a bunch of air particles move to the right, a bunch of air particles move to the left, along with their earlier Brownian motion. You need to understand, kids, that as long as the sound travels by, their Brownian motion doesn't stop. The Brownian motion keeps on happening. Still, within that Brownian motion or the random motion of the air particles, there lies a significant discipline through those air particles, for which they all move back and forth at an orderly fashion that allows the sound wave to travel from one point to another point. এই কথাটা কি বুঝতেছো বলবান?
Yes, sir.
সাউন্ড যতক্ষণ ট্রাভেল করবে ততক্ষণ কিন্তু এয়ার পার্টিকেলস এর বাউন্ডারি মোশন কিন্তু অফ হয়ে নাই। এয়ার পার্টিকেলস এর বাউন্ডারি মোশন তখনও চলবে, বাট সেই বাউন্ডারি মোশনের মধ্যেও আমাদের সাউন্ড সোর্স একটা সার্টেন ডিসিপ্লিন অ্যাপ্লাই করবে, যে কারণে পার্টিকেলস গুলোর মুভমেন্টের জন্য আমাদের সাউন্ড ওয়েভটা ফরওয়ার্ড মুভ হবে। নাও as these air particles move and undergoes compressions and rarefactions, they keep on colliding with each other, and whenever they are in compression, they are in a high energetic state, so they collide with each other with higher speed. As a result, they will become more vigorously vibrated, so their random motion would slowly absorb out the discipline. This is also what happens for the case of a ripple tank. I mean, if you try to visualize this for the case of a ripple tank, if you're trying to produce, for example, if I'm trying to produce a wave at the center of a pond, and then as the wave slowly goes out, the amplitude of the wave slowly dies out. The reason is that as the wave energy slowly goes out, it causes the particles to rub against each other a little bit. they undergo a little bit of friction, and that friction slowly converts into heat energy of the medium, and the wave energy or the kinetic energy of the particles that slowly converts into the heat energy or the random energy of the particles. So that's how the medium actually absorbs the energy out of a wave. It converts its orderly transfer of energy into disorderly or erratic vibration of the particles, and that's how a medium absorbs the energy out of a wave. এই আইডিয়াটা কি বুঝা গেছে বলবান? Now you don't have to ever write
Sir.
this stuff. You don't ever have to write this stuff. So you don't take the load in your head that হ্যাঁ এগুলো ভবিষ্যতে লিখবো কেমন, না এগুলো লিখে লাগবে না। আমি একটা সার্টেন পয়েন্ট অ্যাক্রস করার জন্য এই জিনিসগুলো তোমাদেরকে বলতেছি। হ্যাঁ বলো ইউসুফ।
So sir, it's like they're always random. We are trying to make them not random, but if there is a lot of air, then there will be again random.
I'd say yes. The words are okay. Yes. As long as the sound
Does
happens.
The weight of the air plays a crucial role over here.
I wouldn't say weight. I would say density.
Yes. Sorry. Yes, sir. Density.
I'd say density. So the more particles you're trying to bring into orderly fashion, the more resistance you're going to experience, and the more rapidly you're going to lose your wave energy within that medium. The faster you're going to lose that energy. Now, here's the deal. Whenever the air particles will move randomly, they're going to hit this microphone randomly as well. Or if you are considering your earlobe, if there is no sound in the atmosphere, let's say there is no sound in the atmosphere, so it's a perfectly calm and quiet atmosphere. But what is our ear is designed to do? Whenever the air particles will hit our earlobe, eardrum, then we should sense that as a sound. Now, when there is apparently no sound in the atmosphere, are the air particles which are adjacent to my earlobe, did they stop vibrating or did they stop moving? That answer is a solid no, which means they're actually moving. They are still hitting my eardrum.
Sir.
Let's say you're in a room and there is no apparent sound source around. It's a quiet room. Does this room being quiet means that the air particles which are adjacent to your eardrum are not moving?
No, sir. Absolutely no.
They are moving. They are still moving and they are still hitting in your eardrum, but they are hitting your eardrum at such intensity or at such an disorderly fashion that you are not sensing any sound. But if your ear was really sensitive to each and every single collision that if these air particles actually make to your ear, wouldn't you be able to hear some humming noise even in the most quietest of the room?
Sir, humming noise, sir?
You'd still hear a buzz. That's the point I'm going to make. The reason we don't hear that buzzing noise all the way through, because we are born into it. Our brain learned to discard that buzzing noise as a noise that we have to be within. So it extracts everything other than that buzzing as required information and eventually processes that as actual audible sound. So why am I telling you this? The reason I'm telling you this is that the actual answer of this question is actually this. What this option actually represents, that at the central point we're going to have the highest loudness. Nearest to this, we are going to have the most quiet scenario, but we're not going to have perfect silence. You can see that this part of the graph did not touch the x-axis, did it? It did not touch the x-axis. D number, this one. So let me just zoom in. So what I wanted to see in this D graph, that at the central maximum point, we should have a loud sound, which is perfectly understandable. We have constitutive interference, beautiful. But on the very next one, let's say on this one or on this one, this point did not perfectly touch the x-axis. Not touching the x-axis means what? We are not going to have perfect silence over here, are we? If this graph perfectly did touch the x-axis, which happened on option choice C, if you have a look over here, touching this point perfectly on the x-axis means that we have no sound here whatsoever. At this location, we have absolute silence. But is it possible to achieve absolute silence within atmosphere. Think about it. It's not possible. But then again, so how is it possible to achieve absolute silence? If you want to achieve absolute silence, you have to make it vacuum. And if you make it vacuum, sound waves simply cannot exist. So that would not be a logical choice of medium presence for sound waves. If we still want a sound wave to exist and we want perfect silence can only exist when there is no air particles present whatsoever. So that's why at the point where we are having the first minima, we're not having perfect silence because the air particles do have random motions, and that gives rise to a certain amount of noise. And that amount of noise is basically what this gap represents. Do you understand my point? For the light, this was not the case because light was not affected by the medium almost at all. That's why for the light scenario, we could get perfect darkness at the minima points. This was the case for the light waves. But for the sound waves, they are significantly affected by the medium particles. As long as medium is there, you are going to have some noise available, right? That's why you cannot detect perfect silence. So at this point, we do not have this graph touching the x-axis. That is not happening. Do you understand my point?
So, sir, because another reason why option D is the correct answer is because even though we don't hear anything, there is some intensity.
Exactly, precisely. There is some intensity left. We are not hearing it because our ear is not capable to pick up that sound because it is so weak. But that doesn't mean the sound is not present. If you use enough sensitive microphone, you would be able to pick up that noise. So then what happens? As we go further down at the maximum position, we are losing amplitude. This is perfectly understandable because it's farther away and we are losing a lot of energy. So our maxima, this maxima has a lot less than this one. But here's the deal. Why does this minima is now higher than that? Do you see this? That the second minima has more residual sound than the first minima. Or in other words, I can say that the first minima position is more quiet than the second minima position. Why is that? Why shouldn't they all be at the same level? Yes.
Sir, because the sound waves are spreading, so are the constructive and destructive interferences. So at the point that is farther, the interferences are low. The destructive interferences are much lower compared to where it was closest to the central maxima.
Okay. But why do we have that above the earlier level?
So, normal level reach করতেছে
exactly because of the what Taki said is actually correct, but I'm not sure if he could articulate it to all of you. So let me explain what he just said also in my words. I think this is what he said. As we slowly move away from the central maxima, you have to understand this thing. At the central maxima, the air particles are most disciplined by the pressure waves coming from the two sources. As you slowly go further away, the disciplined movement is slowly become weaker. So what is becoming more prominent? The erratic motion, the Brownian motion, right? Think about it. The air naturally has a certain level of noise. For example, if I wanted to continue this wave further down, how would this wave look like? Let's say we're going to have the same amount of spacing between the central maximas and the minimas. So let's say I'm going to draw some additional lines. So let's say it is minima over here, then it is a bit of a maxima over here, and then maybe the line becomes horizontal at this level. Now have a look. Having a horizontal level of this much noise, this is the natural level of energy within the atmosphere at that temperature. Slowly, because of the two sources within the length of XY region, we are having an orderly fashion of maximas and minimas present. But slowly the sound level of this region is slowly trying to achieve the regular level of noise of atmosphere within that room. It's not trying to be zero because the natural value is not zero. The natural value of sound within, as long as there is atmosphere present, is not zero, because the atmospheric particles, they do have what? Random motion, right? So you do have some amount of residual amount of noise within that room, whether you are asking it or not. So slowly these sound waves are slowly trying to reach up to that natural level of noise, which is somewhat over here. This is why at the maximum point you have a high, and then at the first minima you have the lowest, or you have the quietest location. It is not perfectly quiet, it's not zero sound, it has some unison, but it is the quietest of all the possible locations. Then you have a bit lower than the central maxima, and then the second minima is somewhat a bit more loud than the first minima. This figure is slowly becoming more and more convoluted, so let me just paste it maybe one more time so that you can all see it. Take a good look over here. Do you understand what I'm trying to say? The first thing that I told you, that the way the wave energy transferred to the medium particles is by the the orderly fashion vibration is converted into disorderly vibration, or into the Brownian motion. That's how the temperature of the medium increases and their random motion increases. So as long as there is present, there is a atmosphere present, we will always have some amount of noise. And because of the double-slit experiment, we're going to have an arrangement of loud, less loud pattern, but that would not give us perfect silence, because perfect silence would be only available in vacuum. As long as there is medium present, you cannot have perfect silence. Do you understand now that why this is the correct response for sound and this is the correct response for light? এই জিনিসটা ডিস্টিংগুইশ করা গেছে কিনা?
Yes, sir.
Everyone else?
Yes, sir.
Yes, sir.
Beautiful. So এইমাত্র ইয়েসা বলছো, নাম হচ্ছে গাজী। গাজী, তুমি প্রথমে যে কোশ্চেনটা করছিলে যে we have two of these factors working in play, that's absolutely correct, but for light the distance, the spreading is more or less the only key factor, but for sound both of them are important key factor, and because for sound both of them are key factor, that's why we are not having perfectly destructive, or we are not having perfectly zero intensity because of that medium dependency. I think this answers your question from the earlier part, right?
Yes, sir.
Beautiful. So eta gelo. The next thing that we're going to pick up for today's class is first I'm going to talk to you about leading and lagging wave, what these things are. Okay, so that's a pretty interesting topic to discuss. Where am I? Can I write? Okay, let me just write here. Let me show you the definition first. Okay, this is from physics forums. Have a look over here. Lead means a given wave peaks before the referenced wave. So in your case, the red wave peaks before the blue wave in time. Lag means the blue reference wave peaks and then the red wave peaks at a later time. Acha. All right. Let's say this is our this is one setup for our double slit experiment. Let's say this is our source S, this is our source S1, and this is our source S2. Now I want all of you to look at the screen minutely and see if you can tell me whether this distance is equal to this distance. Are these two distances equal?
Yes, sir.
Do they look equal?
Sorry,
Equal,
equal now.
sir.
Okay, I'll draw for you. It became a curve. Do these two distances look equal?
Converted.
No, no, sorry, equal now.
আচ্ছা কোনটা বড়?
S1 ball.
Beautiful. I was going for this. So as you can see, SS1 is bigger than SS2. Can everybody agree on this? All of us?
Yes.
আচ্ছা এখন মনে করো, let's say we're going to send a wave from here and waves are going to reach over here. Let's say the distance that we have over here is 10 lambda, and then the distance that we have over here is let's say 9.75 lambda. So lambda by 4 less. I have a reason to choose this way. বলতেছি. Let's say we're going to send a wave over here, and we're going to send one specific wave from this point. Let's say a wave forms over here, and this wave starts its journey like by producing lambda distances from here and both ways. It starts from here and is going to reach over here and over here both. On which location does this starting wave will reach earlier? The top one or the lower one?
Lower one.
Lower one.
Lower one. So let's say this wave reaches over here, and when this S2 wave will reach the sent wave from the source S over at this position, how far behind would this wave be from source S1? How far behind? I mean
0.25 level.
0.25 lambda. Beautiful. This is the part that I was trying to look for. Thank you very much for your response. So when this wave is right over here, let's say when this wave right over here reaches exactly over here, I'm going to name this wave as y equals to sine x. This wave is still 0.25 lambda behind the other way. Acha. When this wave will actually reach over here, then this wave would have gone out from this source by 0.25 lambda, right?
Yes, sir.
আচ্ছা এখন আমি এই দুইটা ওয়েভকে গ্রাফে এঁকে দেখাই।
So they're out of phase by 0.025 lambda.
If I use the term out of phase, I should say in radian or degree. So 0.25 lambda would be relevant to how many radians or how many degrees? Get anyone?
90 degrees.
They're out of phase by 90 degree. As বুঝছো?
G sir.
So let's say y1 equals to sine x. Degrees. Okay. এখন when this wave will actually reach over here, this wave would have gone out forward by amount of how much? By and lambda by 4 amount of distance, which means if you consider in terms of crest, let's say the wave that is coming out over here has this many crest. So let's say the wave looks like this. When this crest reaches over here, this wave is still about to receive that same crest for the same number of wave. When that wave reaches within this wave is quarter of a wavelength already out. So who is receiving the wave earlier? Source S2 is receiving the wave earlier, right? When this source receives this wave, and let me just make the sentence, hold up. এখানে স্লাইডার জানি কেমনে অ্যাড করে বলবান?
This was a detailed function in Genesis.
দাঁড়াও, I was trying to make this wave gradually. Wait. Okay. So at t equals to 0, Dude, I'm explanation part ভুলে গেছি. I'm messing up with the equation and graph. আচ্ছা এটা এক্সপ্লেনেশন বাট আমার দেখা লাগবে। আমি তোমাদেরকে নরমাল গ্রাফ করার জন্য কতটুকু জানতে হবে সেটুকু বলি আগে। এক্সপ্লেনেশন পার্টটুকু আমি আবার প্র্যাকটিস করে তোমাদেরকে পরে আবার বলবো যে কেন লিডিং ল্যাডিং এরকম হয় সেই পার্টটা ভুলে গেছি। আইডিয়াটা বলি। If we have two waves on a same graph system and the two waves look like this. Let's say this is our wave number 1. These are wave number 2. Acha. Whenever we have a situation like this, if you compare between their similar parts, for example, if I compare between two crests, the one that has its same phase happening earlier is what we call the leading wave. For example, if you see within this time, this is what we call the leading wave, and the one that is on the front, this is what we call the lagging wave. Now, why do we call them the leading and the lagging wave? The graphical explanation ওই পার্টটুকু আমি মেস আপ করে ফেলছি। There is another way I can go for. সেটা হচ্ছে যে if we have a situation like this, let's say if I label this graph in terms of degree, let's say this is 90 and this is 180, this is 360, and let's say this one is 150. Let me zoom in so that I can write easily. Let's say this is 150. In this case, we can say that waveform 2 is lagging of waveform 1 by 60 degree. This would mean that waveform 2 would be drawn on the right. This same information can also be said in this manner. Now, here's a catch. If you want to compare between this crest, let me use black. If you want to compare between this crest and this crest, how much would be the angle between them? Can somebody tell me? Now, observe carefully. এইখান থেকে এইটুক পর্যন্ত হচ্ছে 360, এইটুকু হচ্ছে 360 ডিগ্রি। তাহলে এই অ্যাঙ্গেলটুকু কতটুকু হবে?
330.
আচ্ছা, let me help you better. এইটুক কত?
So 300.
300 হবে তাহলে।
এইটুক 300 হবে? হাই হাই।
না স্যার, এটা হচ্ছে ইয়ে 60 ডিগ্রি।
এটা 60 আর ইয়ে
আর বড়টা 300।
এবার ঠিক আছে। তার মানে হচ্ছে this information could be also rewritten with the same expression. If I said that waveform, now you can see that if I want to write it in this manner, এখানে একটা জিনিস খেয়াল করো যে waveform 1 এর ক্রেস্টটাকে আমি সামনে ডানে দেখতেছি আর waveform 2 এর ক্রেস্টটাকে আমি পিছনে দেখতেছি, right? If you consider from left to right, which one is on the right? If I consider this crest and this crest, which is on the right? Waveform 1 is on the right, right? বুঝতেছো বলবান কি বলছি? আবার বলি, if I compare between this crest and this crest, which one is on the right? Waveform 2 is on the right, ঠিক? So for that case, waveform 2 is lagging. But if I want to consider this one and this one, for this comparison, which is on the right? Waveform 1 is on the right. Am I correct?
Yes, sir.
because waveform 1 is on the right, so in this case we are going to say waveform 1 is lagging. So I could write that waveform 1 is lagging of waveform 2 by 300 degree. Both of this information are equally correct. Now I want you to understand what this means. এই দুটো ইনফরমেশন কি বুঝছো, ল্যাগিং এবং লিডিং এর কম্পারিজনটা?
স্যার বুঝি নাই।
আচ্ছা, যেই ওয়েভফর্মটা রাইট সাইডে থাকবে দ্যাট ইজ ল্যাগিং অফ দ্য ওয়ান দ্যাট ইজ অন দ্য লেফট। এটা কেন হয় সেই এক্সপ্লেনেশনটা আমি তোমাদের দিই না, আই এম জাস্ট স্টেটিং ইট আউট and take my word for it for the time being. The same waveform part, for example in this case we are considering the crest of the two different waveforms. One is the 1, the other one is 2. Actually এই দুটো ওয়েভফর্ম কে ডিফারেন্ট কালার দিয়ে রাখলে মনে হয় ভালো হতো। আচ্ছা, 1 টাকে আমরা রেড রাখি, 2 টাকে আমি ব্লু বানাই দিচ্ছি।
স্যার আমরা ল্যাগিং লিডিং মানে কেন বললাম স্যার?
এই কেন বললাম পার্টটুকু আমি এক্সপ্লেইন করতে পারতেছি না, কারণ আমি এক্সপ্লেনেশনটা ভুলে গেছি। এটা আমাকে প্র্যাকটিস করে পরে আবার তোমাদেরকে পরে বলবো। এই পার্টটুকু এখন মনে নাই।
আচ্ছা স্যার, একটু ডিরেকশন অফ ওয়েভ এট লিস্ট এটা একটু বলতে পারবেন স্যার?
কোনটা?
ওয়েভ গুলো একটা কি আরেকটার দিকে যাচ্ছে নাকি ওয়ান ইজ মুভিং অ্যাওয়ে ফ্রম অ্যানাদার?
These two waves could be in two different places. These two waves could be in the same places. These two waves could be meeting at the same location on the screen. That they can have a lot of different location. But we have captured two waves happening at the same time instant. মানে হচ্ছে আমরা যদি দুটো ওয়েভকে আমরা যেই টাইম ইনস্ট্যান্টে অবজার্ভ করছি এবং তারপর দুটো ওয়েভকে আমরা সেম টাইম এক্সিসে প্লেস করছি। So in this case t is the horizontal axis. So as time goes by, so this is how the waves behave. We capture the two waves and place them on the same x-axis, and this is what we get. Okay, coming back again, whenever we are comparing two different waves placed on the same time axis or same x-axis, we have to compare between the two waves for two similar part. We can either choose crests, we can either choose troughs, or we can choose positive gradient center or positive gradient negative gradient center. For my example, for the sake of simplicity, I'm using similar part as crest. So I'm going to judge the crest of two different waves for different positions. এই পার্টটুকু আগে ক্লিয়ার হয়েছে কিনা, যে কোনটা লিডিং কোনটা ল্যাগিং জাজ করার জন্য আমি দুটো ওয়েভের ক্রেস্ট গুলাকে আমি জাজ করতেছি। That's the first thing. Now if you observe over here, this the red one is our wave number 1, blue one is the number 2. If you consider between this crest and this crest, which crest is on the right? Waveform 2 is on the right, ঠিক না? In this case we are going to say waveform 2 is lagging of waveform 1, or we can say waveform 1 is leading waveform 2. I could have also said this first information. I could say that waveform 1 is leading waveform 2 by 60 degree. That would be the same thing as this information. Or I could say waveform 2 is lagging off waveform 1 by 60 degree. So the one that is on the right, the crest, we are considering crest. So whenever I'm saying the one that is on the right, I'm actually meaning the crest of waveform 2 is on the right of compared to the crest of waveform 1. So if we compare these two crests within this information, 2 is lagging of 1, or 1 is leading of 2. কতটুকু অ্যাঙ্গেলে? By 60 degree, let's say. এখন কি বুঝা গেছে?
স্যার একটু আবার বলবেন স্যার।
কোন পার্টটা?
স্যার কি বলবো স্যার, অনেকবার ইন্টারনেট চলে যাচ্ছে স্যার, মানে 60 ডিগ্রির আগে মানে স্যার কি বলবো স্যার আমি। আচ্ছা স্যার একটা ছোট একটা সামারি দেন না স্যার এই পার্টের।
স্যার
বলো।
স্যার আমার এখন একটা ক্লাস শুরু হবে 9টার দিকে, আপনি কি এটা রেকর্ডিং ছেড়ে দিতে পারবেন?
আচ্ছা ঠিক আছে,
স্যার লাস্ট ক্লাসে গুলো একটু ছেড়ে দিন তো, আমি ভুলে গেছি একটু দেখার জন্য।
ওকে। না আমি এক্সাম্পল খুঁজে পাচ্ছি না। এটা অ্যাকচুয়ালি ওয়ার্কশিটে এখানে একটা কোশ্চেনে আছে যেটা আমাদের ফিজিক্যালি ড্র করতে হয়। আমি ওটা দিয়ে দেখালে হয়তো তোমাদেরকে ভালো বুঝাতে পারবো। সো ফর এক্সাম্পল কোশ্চেন নাম্বার 5
স্যার
বলো।
তাহলে কোনটা লিডিং কোনটা ল্যাগিং স্যার এটা তো স্যার ফিক্স না স্যার।
হ্যাঁ, এটা অ্যাকচুয়ালি ফিক্সড ইন দ্য সেন্স আমি বলতেছি সেটা হচ্ছে যে ইট অ্যাকচুয়ালি কামস ডাউন টু দ্য পয়েন্ট অফ অবজারভেশন দ্যাট হাউ আর ইউ অবজার্ভিং দিস। If I observe these two waveforms, these two crests which are close to each other and they are separated by a space angle of let's say 60 degree or maybe 1/6 of a wavelength, in that case I can say that waveform 1 is leading and waveform 2 is lagging. But if I go for the bigger distance, if I compare for these two crests, one belonging to waveform 2, one belonging to waveform 1, in that case I can say that waveform 1 is lagging behind waveform 2 by 300 degree. That would still mean the same shape of the graph. মানে হচ্ছে আমি যদি এই ইনফরমেশন দিয়ে মনে করো আমি যদি এই ইনফরমেশন দিয়ে এই মনে করো I have been provided this information and I'm asked to draw the relative position of these two graphs. If I try to draw these two graphs, I'm gonna have to draw two sine curves, one 60 degree apart from another, because that's what it says, and the one that is on the left should be the leading one, the one on the right should be the lagging one. So which means I'm going to say this is my 2 and this is my 1. I'm going to come up with the same original figure that was on the left side. Or if I want to use this information and recreate the whole thing, let's say I'm going to do this. So let's say I'm going to draw one sine wave normally, and then I have to draw another one on the right by separated by 300 degree. So এখান থেকে 300 ডিগ্রি দূরে মনে করো হচ্ছে এই পয়েন্টে। সো আমাকে এখানে একটা ক্রেস্ট রাখতে হবে। সো how this graph is going to look like, somewhat of that sort. বুঝছো কি বলছি? So that this much space between them, বুঝি নাই কেটে গেছে কথা, আবার বলো।
স্যার লাইক উপরের গ্রাফ এই গ্রাফটা সেম হলো না স্যার।
সেম হলো না?
না স্যার amplitude was a cutting distance is same sir y axis and
Exactly. The t value can be different from
Sir,
the two
60
axes,
degree
but
the difference এটা কি fixed স্যার?
with respect to each other they are maintaining the same spacing. এটুকু বুঝছো কিনা?
জি স্যার।
With respect to each other they are maintaining the same spacing. That's basically what the idea of leading and lagging is. বুঝে গেছে?
স্যার বুঝতে পারছি স্যার।
আমি একটা
So sir, this is basically a reflection of the original wave following the other wave by a certain amount. Sorry, a fixed amount.
yes,
Sir, 60 degree কি সব সময় কি ফিক্স থাকবে স্যার?
not necessarily. For other cases we can have 30 degree, we can have 40 degree, we can have 22 degree. It can all vary from place to place. I took up the example of 60 degree because it is a full factor of 360 degree. For example, আমি একটা example দেখাই।
স্যার একটু ল্যাপটপে জয়েন করছি স্যার।
ফর এক্সাম্পল এখানে এই দুটো ওয়েভ থেকে মনে করো এই যে সিনারিওটা আমি আসছিলাম যে this here we had a gap of 0.25 lambda. When these two waves will ultimately meet at the central maximum position, will they meet at the same phase? When these two waves will meet at the likely central maximum position, would they meet at the same phase? The answer is no. There would be a phase difference, there would be a path difference of 0.25 lambda, ঠিক না? Because the two sources are already maintaining a path difference of 0.25 lambda because of the original source discrepancy, because it was not placed exactly at the middle. তার মানে হচ্ছে এখানে যখন আমাদের দুটো ওয়েভ মিট করব, আমি যদি দুটো ওয়েভকে ইন্ডিভিজুয়ালি আমি যদি টাইম অ্যাক্সিস এ প্লট করি, ফর এক্সাম্পল দিস ইজ মাই টাইম অ্যাক্সিস এন্ড দিস ইজ মাই অ্যামপ্লিটিউড অ্যাক্সিস। মনে করো হচ্ছে সোর্স 1 থেকে আসা ওয়েভগুলো যদি এরকম হয়, this is my source this is my source 1, this is my amplitude axis, and this is my source 1 wave. How would the source 2 wave look like? এখন কথা হচ্ছে এই সোর্স 2 থেকে আসা ওয়েভটা লিডিং হবে না ল্যাগিং হবে, ফর দিস এক্সাম্পল এই পার্টটা আমি ভুলে গেছি, বাট apart from that information, this second wave coming from source 2 would be lambda by 4 separated, ঠিক না? It would be lambda by 4
Yes.
4 distance out of phase. So it actually the lambda by 4 হয়, in terms of degree I can write it to be 90 degree, in terms of time period it would be t by 4 whatever. So আমার second যে ওয়েভটা হবে, second ওয়েভটা এটা থেকে 90 ডিগ্রি আউট অফ ফেজ হবে, 90 ডিগ্রি। এখন এই গ্রাফে আমি যদি ইকুয়ালি স্পেস আউট করি, 90 ডিগ্রি মানে হচ্ছে কতটুকু, 0 থেকে 1 হওয়া পর্যন্ত, মানে এইটুকু হচ্ছে 90 ডিগ্রি, ঠিক না?
Yes.
তার মানে হচ্ছে আমার সেকেন্ড ওয়েভটা আইদার 90 ডিগ্রি লিডিং হবে অথবা ল্যাগিং হবে, কোনটা হবে এটা অ্যাকচুয়ালি এক্স্যাক্টলি ভুলে গেছি। ফর দ্য টাইমিং লেটস সে আমার এই সেকেন্ড ওয়েভটা হবে হচ্ছে 90 ডিগ্রি লিডিং। সো 90 ডিগ্রি লিডিং হয়, তার মানে হচ্ছে আমার এটা হবে S1 টা হবে হচ্ছে ল্যাগিং ওয়েভ। তার মানে তার আগে অন দ্য লেফট আই হ্যাভ টু ড্র আ ক্রেস্ট ফর দ্য সোর্স 2 বাই আ ফেজ ডিফারেন্স অফ 90 ডিগ্রি। তার মানে হচ্ছে আমার এই ওয়েভটা হয়তো দেখতে হবে হচ্ছে এরকম, এই, তারপর আবার এখানে হচ্ছে এই, তারপর এখানে হচ্ছে এই, তারপর এখান থেকে হচ্ছে এই। So that's how these two waves are going to work out. At the likely center maximum position, they're going to have a phase difference of 90 degree because they were separated by path difference of lambda by 4. Now, if you wonder, can we call this point central maxima? The answer is no. We are not going to call this point central maxima because we are not going to have the bright spot over here. The bright spot is going to be located somewhere else where these two waves perfectly merge on each other. যে পয়েন্টটাতে আমাদের দুটো ওয়েভ পারফেক্টলি মার্জ করে, আমরা ওই পয়েন্টটাকে সেন্ট্রাল ম্যাক্সিমা বলি। যেখানে দুটো ওয়েভের মধ্যে কিছু একটু হলো আছে, সেই পয়েন্টগুলোকে আমরা সেন্ট্রাল ম্যাক্সিমা বলি না। ওকে,
সো সরি, এই সিনারিওতে স্যার সেন্ট্রাল ম্যাক্সিমা বলে কিছু নাই এখানে স্যার?
হ্যাঁ আছে, সেটা আমাদের স্ক্রিনের এক্স্যাক্টলি মিড পয়েন্টটা হবে না, অন্য কোনো একটা পয়েন্টটা হবে। ফর এক্সাম্পল এটা তো 0.25 ল্যাম্ডা পিছনে আছে, তাহলে এটাকে 0.25 ল্যাম্ডা বেশি কভার করতে। ফর এক্সাম্পল the central maximum will be somewhere over here. Let's say the central maximum will be somewhere over here. In such a way, let's say if this much path is x and this much path length is x plus 0.25 lambda, if we find out a point of this point, this would be our central maxima. So that 0.25 lambda and that 0.25 lambda are matched up so that you have a perfect phase over here, but not at the geometric midpoint. এই midpoint এ perfect central maxima হবে না, বুঝছো কি বলছি? যেই লোকেশনে দুটা ওয়েভের ফেজ পারফেক্টলি আবার ম্যাচ হয়ে যাবে বা তাদের প্যাথ ডিফারেন্সটা 0 হবে ফ্রম দ্য অরিজিনাল সোর্স, ওই পয়েন্টটাতে আমাদের সেন্ট্রাল ম্যাক্সিমা ক্রিয়েট করবে। বুঝা যাচ্ছে না? I'll take a small break. I'll be right back. So এই হচ্ছে লিডিং ল্যাগিং এর কাহিনী। Okay, the next thing that we have is what we call diffraction grading. ডিফ্রাকশন গ্রেডিং প্রতিদিন পড়াবো, আজকে ডপলার ইফেক্ট পড়াই। ডপলার ইফেক্ট is nice. Doppler effect happens due to the relative speed between the source and the observer. Why does it happen? If there is a source of wave, let's say I'm going to use sound source. So if there's a source over here and there's an observer, so I'm going to label this as source, this is observer. There they have zero velocity between them, zero relative velocity, which means they are perfectly stationary with respect to each other. They might both be moving in the same direction. They might be actually stationary. Doesn't matter. As long as their in between distance is not changing over time, this source will be emitting a certain number of waves per second, and the observer will also experience the same number of waves per second. So if the source's frequency is f, the observer will also perceive the source to have a frequency of f, not anything different. So if this f is, let's say, 1000 hertz, the observer will perceive the source is emitting waves at perfectly 1000 hertz. But that would not be the case if any of them is moving with respect to each other. For example, let's say if the observer
এখন বুঝি নাই স্যার
বুঝি নাই,
মানে স্যার জিনিসটা বুঝলাম না স্যার আপনি কি 1000 হার্টজ বলছেন
if they are not moving with respect to each other, if the source is stationary and the observer is also stationary, and the source is producing waves at 1000 hertz, the person will also experience the source to have 1000 hertz frequency. Because if the source is producing 1000 waves per second, the observer would still experience 1000 waves crossing him every second. So he will perceive the source to have 1000 hertz, exactly the same as the original frequency. That's the normal scenario when they are not moving with respect to each other.
স্যার এখানে স্যার মানে এই ইমিটার অবজার্ভ এখানে এক্স্যাক্টলি মানেটা কি বুঝলাম না স্যার মানে মানে what can we visualize about this?
For example, I'm talking to you from a distance of 10 meters, and we are both standing
Yes,
perfectly
sir.
stationary, and we're not moving. So if I say at a certain frequency, you'll be hearing the exact same frequency, but maybe at a lower volume because you are a bit far away from me. But the observed frequency should be exactly same. You will not hear a different frequency. Because if I'm producing a certain number of waves per second, that same number of waves per second will be crossing across you.
Sir, is it always for moving away, naki moving closer
No.
or something?
In this case, I'm just telling you that if none of them are moving, I'm starting with that. But things would be different if they were moving about each other. Have a look.
The Doppler effect. In Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you,
Do you see that the wavelength is smaller over here and the larger over here?
Yes.
Yes,
Because the
sir.
car is moving forward. So, but the speed of the sound through air is remaining the same because it's still the air. So which means anything that is observed in front of the car would be experienced as a smaller wavelength / higher frequency. Anything that is observed behind the car would be perceived as a longer wavelength / lower frequency, correct? The source is not emitting a different frequency. The source is emitting the same frequency, but because it is moving in front of the car, the waves are getting crunched. They are getting squashed. Behind the car, the waves are getting spread out. That is causing this person to perceive two different frequency, like that. So as the car approaches, he experiences higher frequency. As the car leaves, he experiences lower frequency. Hear the sound?
The horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Amazing video. কিছু বুঝা গেল?
জি স্যার বুঝছি
স্যার
স্যার
অনেক কিছু বুঝা গেল স্যার। স্যার
স্যার ওইটা তো একটা কোয়েশ্চেন
বলো হাসান বলো।
স্যার ওই যে দ্যাট মিন্স টেকনিক্যালি দ্য ইউনিভার্স ইজ এক্সপ্যান্ডিং মানে লাস্টে যেটা বলছে আর কি।
Yep, precisely. So you can also see this one. They pretty much all have the same explanation. Yes, bolo.
Can it also be like, rather than the universe being expanding, it is like the Earth's rotation, because of which we are seeing different frequency of light?
ওইটা তো হবে না স্যার, বিকজ এটা তো এক সানও তো রোটেট করতেছে থ্রু দ্য মিল্কি ওয়ে, ওইটা তো হবে না।
This is not applicable because of the rotation of the Earth. I mean, considering that Earth's rotation has some speed, and it's actually it takes 24 hours to go around the whole orbit. We do have some actual speed with respect to our surroundings, considering the whole cosmic environment. But we can, even if we take that out mathematically out of our situation, for example, the primary observation for the Doppler effect, the redshift, was actually observed by Hubble telescope, and from that incident, the scientists came up with the idea of the redshift, that most of the stars that we are observing, they are appearing to be of a color that is more close to the red, and stars which are observed, which are observed 10 years earlier and which are observed right now, they tend to have their color changing towards more red, which tells us that they are now getting away from us at a much higher speed than earlier. That actually gives us the idea that the whole universe is actually getting far apart from each other, which basically is the whole concept of something getting exploded. So whenever something explodes, all the individual particles actually move apart from each other, and the farther they are, the faster they move away. That gives us the whole concept of Big Bang in the first place.
স্যার
হ্যাঁ বলো।
স্যার আমরা যদি একটা কার নিই, একটা ব্লু কার, ওটাকে অনেক হাই স্পিডে মুভ করি আর জুম ইন করে রাখি আর অনেক দূরে যাচ্ছে, মানে আমাদের রিলেটিভ ভেলোসিটি আমাদের থেকে অনেক দূরে যাচ্ছে, তাহলে ওইটা আস্তে আস্তে রেডিশ হয়ে যাবে না?
Yeah, it would well, reddish in this case mean that the original frequency observed would become less than what its actual frequency is. So if it was blue, it might actually start to look a bit more blue এর নিচে হচ্ছে কি vivi or blue এর নিচে হচ্ছে green, then it might look a bit yellower. It means the observed frequency will become less, move towards the red.
স্পিডে যদি গাড়ি থেকে টর্চ দেখায়, তাহলে স্যার তখন তো স্যার ডিফারেন্ট কালার দেখায় না স্যার?
Well, that's because our biological eye has a limit of understanding. How much information that can our biological eye can visualize is far too small for the light waves, because the typical frequency of a light wave is within the scale of 10 to the power 6, 10 to the power 7 hertz. So ওই variation বুঝার জন্য আমাদের eye appropriately equipped না. However, for sound it works much better, because whenever a car moves across us or any sound source moves across us, the change in frequency can be significantly high, and our ears can decipher that difference. But for light, our eyes cannot, our naked eye cannot perceive that difference. But with appropriate equipment, we can do that. বুঝা গেছে?
Yes, sir.
আচ্ছা, ডপলার ইফেক্টের জন্য আমাদের বেসিক্যালি দুই সেট ইকুয়েশন আছে। দুই সেট ইকুয়েশন থাকার কারণ হচ্ছে যে সাউন্ড ওয়েভ এন্ড ইলেক্ট্রোম্যাগনেটিক ওয়েভস দে হ্যাভ ডিফারেন্ট টাইপ অফ বিহেভিয়ার ফর ডপলার ওয়েভস। আমাদের এই ফুল ডিসকাশনটা সিলেবাসে নাই, বাট দুটো ডিফারেন্ট ইকুয়েশন আমাদের সিলেবাসে আলাদা হয়ে দেওয়া আছে। একটা হচ্ছে ফর সাউন্ড ওয়েভ the apparent frequency is the observed frequency. I'm going to write that as f prime is given by a certain fraction multiplied by the source's original frequency. And এই ফ্র্যাকশনটা কি হবে? এই ফ্র্যাকশনটা হচ্ছে এরকম, the situation is like this.
Sir, it's F prime, sir.
বলতেছি VW means the speed of the wave, for example the speed of the sound. VO means the speed of the observer. So VO is applicable when the, let's say, the source is stationary, the observer is moving with respect to the source. And VS is, let's say, the observer is stationary and the source is moving towards or away from the observer. সো সোর্সের স্পিডটা আসবে নিচে আর অবজার্ভার স্পিডটা আসবে উপরে। এখন কথা হচ্ছে যে আমরা কোন সময় প্লাস করব কোন সময় মাইনাস করব এটা কিভাবে বুঝবো? দিস কামস ডাউন speed of the source.
Okay, sir.
This comes from the very basic idea of whether they're getting closer or they are getting farther apart. Let me just bring this up easier to you. Whenever the two things, let's say the source and the observer are getting closer, and getting closer দুই ভাবে হতে পারে, অবজারভারও সোর্স দিকে মুভ করতে পারে অথবা সোর্স অবজারভার দিকে মুভ করতে পারে, রাইট? দুটোর যে কোনো একটা হতে পারে। সো দুইটাও সাইমালটেনিয়াসলি হতে পারে, সমস্যা নাই। সো ইফ দিস ইজ হ্যাপেনিং দেন উই শুড, দ্য অবজারভার শুড এক্সপেরিয়েন্স a bigger frequency than the original frequency, whereas if the source and the observer are getting away from each other, for example the observer is moving away or the source is moving away from the observer, in that case the observed frequency would be less than the original frequency. এই কনসেপ্টটা আগে ভালো করে বুঝো। Getting closer, higher frequency observed; getting further away, lower frequency observed. If you can remember this information, which is a very basic idea of Doppler effect, this equation can be very easily chosen for the plus or minus sign. For example, in a case where the source is stationary and the observer is getting closer, in that case the observed frequency should be higher than the source, which means the value of this fraction should be bigger than 1 or smaller than 1. বলো তো, if this frequency has to be, f prime has to be bigger than f, এই ফ্র্যাকশনটার ভ্যালু কি হতে হবে? মোর দেন 1 হতে হবে না লেস দেন 1 হতে হবে?
মোর দেন 1 হতে হবে।
মোর দেন 1 হতে হবে। মোর দেন 1 হতে হলে আমাদের নিউমারেটর কি হতে হবে? বড় হতে হবে না ছোট হতে হবে?
নিউমারেটর বড় হতে হবে।
নিউমারেটর বড় হতে হবে। সো যেহেতু সোর্সের ভ্যালু 0, সেখানে আমি কিছু লিখলাম না। যেহেতু গেটিং ক্লোজার, তাহলে অবজারভার স্পিডটা উপরে কি হবে? অ্যাড হবে। বুঝছো কি? দ্যাটস দ্য চয়েস। আর যদি এরকম হতো যে অবজারভার ইজ গেটিং অ্যাওয়ে,
স্যার তাহলে ভিএস বড় হবে স্যার, মানে প্লাস হবে স্যার?
না, vs 0. Observer source stationary. In this case I'm talking about the observer is moving. is observer is getting closer তখন প্লাস হবে, is observer is getting further away তখন উপরে মাইনাস হবে। Alternately মনে করো observer stationary এবং source মুভ করতেছে, let's say in other case let's say the source is moving where the observer is stationary, তখন যদি getting closer situation হয়, কোশ্চেন পড়ে যদি বুঝা যায় যে they are getting closer, তখন ডিনোমিনেটর হইতে হবে ছোট। For closer scenario VW উপরে VW থাকলো, নিচে হবে হচ্ছে সাবট্রাকশন, আর উপরে হবে হচ্ছে, আর যদি ফার্দার অ্যাপার্ট হয় তখন ডিনোমিনেটর হইতে হবে বড়। এই হচ্ছে প্লাস ও মাইনাস গুলোর চয়েসের ভ্যারিয়েশন। So it all comes down to the point that what are you trying to get at? Are you trying to find out a bigger frequency, or are you trying to get a smaller frequency? এটার উপর বেস করে আমাদের সাউন্ডের ফর্মুলা হচ্ছে এই জিনিসটা, এই ফর্মুলাটা। আর যদি আমরা লাইট নিয়ে কাজ করতে চাই, ওখানকার ফর্মুলাটা আরো সিম্পল। লাইটের ফর্মুলাটা হচ্ছে এরকম: the change frequency, the difference in frequency observed divided by the source frequency should be equals to the relative speed between the two things, source and observer, divided by the speed of light. এটা হচ্ছে লাইটের ইকুয়েশন, and the observed frequency would be equals to f plus or minus delta f. এখন যদি if they are getting closer তাহলে প্লাস হবে, if they are getting farther away then minus হবে। So change in frequency divided by source frequency equals to relative speed divided by light speed, and the observed frequency would come from the plus or minus delta f, that is the different variation of the frequency with respect to the original frequency. And if they are getting closer তখন আমাদের delta f টা প্লাস করা লাগবে, if they are getting farther apart then আমাদের delta f টা মাইনাস করা লাগবে। এটা হচ্ছে লাইটের জন্য। বুঝছো কি বলছি?
স্যার
বলো হাসান।
স্যার আমাদের স্কুলে একটা ফর্মুলা দিছিল স্যার, fs equals to f naught divided by f plus velocity of source, v velocity plus velocity of source.
একবার বলো।
Sir, f observed, frequency observed equals to frequency of source divided by velocity of wave plus or minus sir নিচে এটা না স্যার, নিচে হচ্ছে vw plus minus velocity of vs.
হ্যাঁ,
এটা কোনখানে অ্যাপ্লিকেবল স্যার?
আমি তো এটা লিখলাম, এই যে
স্যার ওটা f naught ছিল স্যার উপরে স্যার।
f prime basically means the observed frequency, f means the source frequency or the original frequency. This is the one that is getting varied. So তোমাদের স্কুলে ওই অবজারভারের পার্টটুকু উপরের টুকু লিখে নাই, শুধু নিচের টুকু লিখছে, বাট উপরের টুকু আসতে পারে। This formula was given exclusively for the case of when the source is moving with respect to the observer. The observer is considered stationary, but that's not always the case. Sometimes the observer can also move towards the source.
জি স্যার, তার মানে আমাদের হচ্ছে velocity of the wave which divided by the depends on the relative velocity, ওই যে আমরা closer না farther apart ওইটা দিয়ে বুঝতে পারবো।
Precisely. So are you trying to get a fraction bigger than 1, or are you trying to get a fraction smaller than 1? ওই চয়েস থেকে আমরা প্লাস মাইনাস গুলো বুঝতে পারবো।
জি স্যার।
ঠিক আছে,
একটু
হ্যাঁ বলো ইউসুফ।
ইকুয়েশন গুলো একটু উল্টা পাল্টা করতেছি এখানে। স্যার নিচের এই পার্টে স্যার কোনটা স্টেশনারি স্যার? সোর্স স্যার।
স্যার
হ্যাঁ বলো, আরেকটা ক্লাস আছে তোমাকে ছেড়ে দিচ্ছি আমি।
একটা ক্লাস স্যার।